So in section 1, we're just going to look at, in general, what it means to be a sequence, okay? We're going to write the terms of a sequence expressed by what's called a recursive formula. And we're also going to look at explicit formulas as well and be able to write the terms of a sequence in an explicit formula also, all right? So a sequence is defined to be a function whose domain is the set of positive integers, okay? The set of positive integers. Typically, your first input value is 1, then your second input value would be 2, 3, 4, etc. Okay? You can use function notation here, but quite often instead of f of n, we also will just use the notation a sub n. And you're going to see that the letter n is a very common letter that's used for sequences and series, okay? So f of n or a sub n, they mean the same thing. And let's say we set them equal to 1 over n. So f of n equals 1 over n, or a sub n equals 1 over n. That is an explicit formula, and we are letting n be a positive integer. So if n is 1, I could represent that with the notation a sub 1 or f of 1, and that represents the first term of the sequence, okay? So using the formula, if n is 1, then 1 over n would become 1 over 1, which is 1. Now let's say I wanted a sub 2. This would be the second term of the sequence, where n is 2. So the formula would yield 1 half. A sub 3, where n is 3, would yield 1/3. And I could continue this process with, any value of n that I want, right? Now, notice how we have this written. It's very common to write the terms of your sequence in a set notation where you use braces. So we just put them in order by n value. So your first term is 1, your second term is 1 half, your third term is 1/3, and so forth. Okay? Now, once again, this is an example of an explicit formula. A sub n equals 1 over n is an explicit formula. It defines the nth term or the general term of a sequence using the position of the term. And the position of the term is represented by n itself. Okay? So I have another explicitly defined sequence below. A sub n is equal to n minus 1 over n. We want the first 3 terms. The first term would be represented by a sub 1, where n is 1. Okay, that means I would get 1 minus 1 over 1, which is 0 over 1, or 0, right? If I want the second term, that would make n 2, and it would be represented with the notation a sub 2. That would yield 2 minus 1 over 2, which is 1 over 2, or 1 half. And if I want the third term, n is 3, that would be represented with the notation a sub 3. 3 minus 1 over 3 yields 2/3. So my first 3 terms here would be 0, 1 half, 2/3. Any questions there? What would the next term be? Three-fourths. Yeah. The fourth term would be 3/4. The fifth term would be 4/5. Sixth term would be 5/6, so forth. So there's a definite pattern at play. Okay, now let's kind of go in the other direction. Here you're given the first 4 terms of a sequence, and you want to come up with an explicit formula. That is, find a sub n for each sequence. So let's say my first 4 terms are 1, 4, 7, and 10. 1, 4, 7, and 10. Notice there's a pattern there, right? To go from 1 to 4, from 4 to 7, from 7 to 10, what am I doing? You're adding 3 each time, okay? Now, repeated addition yields multiplication, doesn't it? Repeated addition can be represented with multiplication. So, I'm going to start here. I'm going to say a sub n is equal to 3n. Why 3n? Because I'm continually adding 3. Now, 3 in itself is not enough, because clearly if I make n 1, 3 times 1 is 3, but I need the first term to be a 1. So what should I tack on after 3n to make that happen? Owen, what'd you say over there? Yeah, let's do this. Now check to make sure that works for the other terms. The second term is 4. So if I plug 2 in for n, 3 times 2 is 6. 6 minus 2 does give me 4. The third term is 7. N is 3. 3 times 3 is 9. 9 minus 2 is 7. Okay? This is an example of an arithmetic sequence. Okay? Arithmetic. And we're going to look at these in a lot more detail later, but just for now, know an arithmetic sequence is when you're continually adding the same number repeatedly. Okay, next one. First 4 terms are 5, 8, 11, and 14. So we kind of have the same pattern here, don't we? We're adding 3 each time. So I'll begin the same way with a sub n equals 5n. Or I'm sorry, 3n. Okay, what do I need to tack on this time so that the first term ends up being a 5? Plus 2. If n is 1, 3 times 1 is 3. 3 plus 2 will give me 5. If n is 2, 3 times 2 is 6. 6 plus 2 does give me 8. So this is another example of an arithmetic sequence, right? Okay, bottom left. First 4 terms are -1, 4, -9, and 16. Now, ignore the negatives for a moment. If you just looked at the absolute value of each of those, you would have 1, 4, 9, 16. What do we know about all those? They are perfect squares, right? Perfect squares. So it stands to reason we could do an n squared as part of our explicit formula. Now, we have to consider that there's a sign change every other term, though. So clearly, if I plug in 1 right now for n, 1 squared is 1, but I need it to be -1. Okay? So this is very common for sequences to be presented this way, where every other term the sign changes. Here's how we would account for that. Take your n squared, and you're simply going to multiply it by a -1 raised to the power of n. Okay, now, see if it works for each one of these. When n is 1, let's actually write this out. A sub 1, that would be -1 to the first times 1 squared. What's -1 to the first? -1 to the first. -1, right? 1 squared. 1. -1 times 1, -1. Let's try a sub 2. That would be -1 to the second times 2 squared. What's -1 to the second power? +1. And then 2 squared is 4. So 1 times 4 gives me 4. So it seems to be working, right? Okay, now look at the final sequence in the right there. 1, -4, 9, -16. So it's the same perfect squares. It's just now the signs are changing on the even numbered terms rather than the odd numbered terms. So here's how I count for that. I can use the exact same formula with one slight change. Instead of taking -1 and raising it to the power of n, we're going to do n plus 1. N plus 1. Now let's check and make sure that works. A sub 1 would be -1 to the power of 1 plus 1 times 1 squared. That's -1 to the second power times 1. -1 to the second is 1. 1 times 1 is still 1. So see how by adding that 1 to n, it's changing the power on -1 from being odd to even, so that the sign will change when I raise -1 to the even power. It'll change it back to positive. Okay? So again, this is very common with sequences for us to change the sign on every other term. So don't overcomplicate this. If it's the odd numbered terms that have a negative to them, you're going to do -1 to the power of n. If it's the even numbered terms that have a negative power to them, you're going to do -1 to the power of n plus 1. Okay? Now, there are other ways of doing this. Instead of doing n plus 1, I could have done like n plus 3 or n plus 5 or n plus 7. It really doesn't matter as long as I'm getting -1 to be raised to an even power rather than odd power. Yeah. Say that again. -1. Okay, like this.
Yeah. So it's and then times and to the -1 to the n.
Times -1 to the n. Like so?
Yeah.
Let's see. So that would be a sub 1 would be -1 times n squared, or 1 squared, times -1 to the first. So that's -1 times 1 times -1, which is going to end up being 1. So that will work. I would say it's a little, it's not simplified because notice you have -1 to the first power and then -1 to the power of n. You can use a property of exponents on those, and you can add their exponents together to say that that's -1 to the power of n plus 1, which is ultimately what we have. Okay. Now, it's not an incorrect explicit form. It's just not simplified. Yeah. All right. Other questions? Okay.